minus T1 cosine 30. Just kidding, 37. Again, since this is at equilibrium, this should be equal to 0. So that means I could rearrange this to say T2 cosine 53 equals T1 cosine 37. Okay, but more often than not, we use the sum of the forces in the x direction to substitute something else in whenever we get our sum of the forces in the y direction. So let's just say either T1 equals all of this or T2 equals all of this, okay? So maybe let's just do that for, I don't really care. Let's do that one for T2 since it's just on the other side. So then T2 would equal T1 cosine 37 over cosine 53. So that's just the sum of the forces then in my x direction. Okay, and then I'm actually going to make this a little bit cleaner because if I take cosine 37 and divide it by cosine 53, I would get T2 equals 1.33 times T1. So this is just a little bit of a cleaner number. Okay, but again, it doesn't tell me what T1 is, and I still haven't solved for what T2 is. So I need then to clearly do another step. So let's do the sum of the forces in the y direction now. So the sum of the forces in the y direction is equal to T2 times sine 53 plus T1 sine 37 minus T3, which we already found out is 122 newtons. Since it's at equilibrium, that all equals 0. So then really, T2 sine 53 plus T1 sine 37 is equal to 122 newtons. I could plug in now, I can substitute in for T2 that's equivalent to 1.33 times T1. So let me do that. So I know T2 is equal to 1.33 times T1 times sine 53 plus T1 sine 37 equals 122 newtons. Okay, so when I do this, I should get 1.06 times T1 plus 0.602 times T1 equals 122 newtons. So then my 0.602 plus my 1.06 will give me 1.66. The smaller 2. Okay, so this gives me 1.662 times T1 equals 122 newtons. So then let me divide then both sides by 1.662, so then that way I can get T1 just by itself. So if I do that and take 122 and divide it by 1.662, I get that the first tension, the one that's at the 37-degree angle, is 73.4 newtons. Will that cable break? That was my goal. That cable's not going to break because it said it would only break if it exceeded 100 newtons. So this cable won't break. It only has 73.4 newtons in it. But I need to find T2. So to find T2, I know T1, so let's just plug it back in here to the really simple equation instead of plugging it back into the longer one. So T2 equals 1.33 times T1, 73.4. Okay, if I do that, I should get, what is that, 97.6? Okay, and then T2 is also less than 100 newtons, so that one also will not break. So T1 and T2 could not exceed 100 newtons, and they don't, so I don't have to worry about the traffic light crashing down on my car as I drive underneath it. So this is just showing us how we can do an equilibrium problem. So I set up the sum of the, first of all, if I have a traffic light with 3 different cables, I always find that T3 one, whichever one is connected to the mast, I find that one first. So we did that. I know that it's an equilibrium, so it's 0, so I can say the weight of that light, or whatever the object is equal to the tension in that direct string that's attached to that object. Next, I want to find the tension in both of these cables that are at whatever angles, so I set up the sum of the forces in the x, and I get some type of an equation that I can use to substitute in to my sum of the forces in the y. Okay, so I always do the one that's connected to the object first, set up the sum of the forces in the x, set up the sum of the forces in the y, substitute in, and then that way you can get your tensions. Okay, and that's how those types of problems will always work. Okay, let's let this one be our last problem here. So it says a car of mass m is on an icy driveway inclined at an angle. Find the acceleration of the car assuming that the driveway is frictionless. So I have a car on some type of incline here. So let's draw the free body diagram of that. So I have my car on my incline, we'll call that theta. So there's no numbers here, they just want us to show this using symbols. Okay, so free body would be weight force going straight down. Normal force is going to be perpendicular to the surface, which is totally not perpendicular to that surface, but it's good enough. And I know that it's going to have some acceleration as it's moving down the ramp. I need to change this. This is going to bother me. Okay. So again, I would prefer it that you always just take your weight force and then kind of skew that axis based on where my weight force is. So the normal is going to be along the y-axis, and then that's going to be my x-axis there. So my weight force is what I'm going to break up into components. So I'm actually just going to break along the y-axis here, and theta will be here. Okay, so I need to find acceleration, and to find acceleration, or just an equation for acceleration, because that was my goal, find the acceleration of the car, what force is causing the acceleration of the car? That's the biggest question now. If the normal force and then the y component of weight force are in that y direction, they're in that vertical direction, and my car is accelerating horizontally along the x-axis, then the normal and the y component of weight are going to be balanced. They're the ones that are going to equal 0 if I set my sum of the forces in the y up. The only x force that I have then that's in play is the x component of the weight force. So if I want to write sum of the forces in the x direction is equal to mg sine theta, because it's the component in the x, so mg sine theta, and that's equal to mass times acceleration. Because I have an acceleration, they're asking me to find it, I just want to do it finding symbols. So I just want to get acceleration all by itself. So to do that, let's divide by mass. When I divide this both sides by mass, I see that the masses here cancel. So really acceleration is equal to acceleration due to gravity times sine theta. So technically speaking, when a car is sitting on an incline, its acceleration doesn't have anything to do with its mass. It is independent of the mass of the car. Instead, it depends on the acceleration due to gravity and then whatever the angle is of that incline. That would be a great conceptual question to ask you, and because I can prove that using this type of symbolic mathematical calculation here. Okay, so that was the first part of my question. The second part of that question, so we found the car's acceleration. The second part says, suppose the car is released from rest at the top of the incline, and the distance from the car's front bumper to the bottom of the incline is d. How long, so I want to find a time, how long does it take the front bumper to reach the bottom of the hill, and what is the car's speed as it arrives there? So my goal is to find time, and then my next goal is to find final velocity, final speed, because it says what is the speed as it arrives at the bottom of the incline. So I want to find VF, and I want to find time. Actually, let's go back here. Okay, well I know already that acceleration for this one is equal to g times sine theta. So we know acceleration, but what are some other things they told us? We know that it started from rest, so vi is equal to 0. I know that it's going to have some displacement, so I know that it has a displacement d. I know acceleration is equal to g sine theta, and my goal is to find time. That's my first goal. What is time? So I want to think kinematics here. So all of the ones that incorporate a kinematic with this would be displacement is equal to vi times t plus 1/2 a t squared. Okay, I'm going to leave this as d because the displacement they told us is just going to be represented as d. So d equals, vi was 0 times time, which is really just going to be 0. So I'm just going to pretend like this doesn't exist anymore because this is just going to be 0. So then 1/2, I know that a is equal to g sine theta, so let me plug that in. So 1/2 g sine theta t squared. Well, my goal isn't to say what is the displacement equal to, my goal is to say what is time equal to. So let me rearrange all of this now for time. So if I do that, I would be left with, so I had 2d over g sine theta equals t squared, but really then that would be the square root. So t equals the square root of 2 times the displacement, whatever distance traveled, divided by g sine theta. That will be my time. So I now answered one of the questions, but now I have one more question, and that is, what is the final speed? Okay, so again, I was given all of this. I also want to know VF. So instead of using anything with time, because I really don't want to have to deal with this, is there another kinematic that would be easy to use based on VF, A, D, and VI? And that's one that I think a lot of people kind of forget about, and that's the VF squared equals the VI squared plus 2AD. My goal is to find VF, so I have VF squared equals, VI was 0, so I'm just going to eliminate that, times 2 times A, which was g sine theta, and then times D. So then if I just want the final speed, it would be the square root of that. So VF equals the square root of 2g sine theta d. So we found acceleration, we found time, and we found final speed all just using our variables here. And what we learn most in this one is that as I'm thinking about the acceleration of an object as it's moving down an incline, it's independent of its mass. And I know that because the masses ended up canceling out here. So it's really just dependent on theta and then that acceleration due to gravity. Okay? Awesome. So we're going to stop here. And I'm going to have a couple problems that I'll post that you should try. And I'm going to post those if I don't see you I'll post them on Friday. So if I don't see you on Friday because of the senior breakfast, make sure that you look at your blog over the weekend. There'll be a couple problems. And then if I do see you, then we'll go over all the problems that we wanted to go over in multiple choice from here. If not, I'll see you on Monday, guys, and you have a really wonderful weekend. Bye!